And coming up right now is the Space Show.
The sounds of the Bayside, 88.3 Southern FM.
Welcome to the Space Show, presented by members of the Space Association of Australia. Hello, I'm Andrew Rennie, and on the panel and mission control, we have Richard. And here on the Space Show, we're turning back time 15 years to 2011, August the 5th. That's when a NASA spacecraft called Juno was launched towards Jupiter. Well, it arrived in Jovian orbit in 2016, July the 5th. That's 10 years ago. And it is still operating. 1 year ago, a conference was held in Europe at a briefing, and we're going to take you there now.
Good afternoon, everybody, and welcome to our third press conference of this General Assembly. The European Geosciences Union is the largest European geoscience conference in Europe and the second largest in the world, where this year we have more than 20,000 people both on site and virtually joining us. So today's press conference is a Juno mission briefing by NASA. And we have Scott Bolton from the Southwest Research Institute, Shannon Brown from Jet Propulsion Laboratory, Alessandro Mura from the National Institute of Astrophysics in Italy, and last but not least, we have Yochai Casby from the Weizmann Institute of Science in Israel. And now I'm going to hand the floor over to Scott Bolton.
Okay, thank you very much. So we're here to present to you the latest results from the Juno mission spacecraft. It's solar powered. There's 3 giant solar arrays, and this spacecraft cartwheels through space. So that's spinning twice per minute, and it makes all the observations that we're going to talk about in order to get our results. And so we're actually in orbit around Jupiter today. Next week, we will go by Jupiter. We go very close every 30 days or so. And next week will be the 72nd orbit. We arrived at Jupiter back in 2016. We launched in 2011. And so we've gone through 71 orbits, to date. And next week will be the 72nd one. And so the results you're going to hear about today are a number of different, topics. And the first speaker will be Shannon, and he'll be talking about results of the moon Io, which is the most volcanic body in the solar system. And in particular, he's going to be talking about results from an instrument that we call the microwave radiometer, MWR for short. And this is an instrument that was invented in order to see through the cloud top. So you see these incredible clouds of Jupiter, and this instrument was designed in order to be able to see through those cloud tops down deep into the atmosphere, and to understand the dynamics, and more importantly, the composition of Jupiter in order to help us understand how it formed and evolved. But he's going to be talking about the application of that instrument when you pointed it at Io. So over the course of Juno's lifetime, our orbit has slowly evolved. And during the prime mission, we avoided all the satellites, and we only went through and studied Jupiter. And we mapped it out. We made a lot of different kinds of science associated with understanding Jupiter, the body, and its magnetosphere. However, during the first extended mission, which started in 2021, the orbit had been moving and migrating naturally because of Jupiter's gravity field. Jupiter is oblate, which means that the middle of Jupiter is a little bit fatter than its poles, and that twists our orbit around. And that allowed us to eventually pass by the Gauland satellites, Ganymede, Europa, and Io. Shannon's going to talk about the application of this instrument that sees through the atmosphere, what it did when it looked at these satellites, and in particular Io. When we looked at Europa and Ganymede, we actually could see through some of the ice, and that was the first results of a resolved picture of what the subsurface ice looked like on Europa and Ganymede. When we pointed to Io, it wasn't so clear what we'd see because it's mostly rock. And we thought, well, maybe we won't see anything, but he's going to talk about results that surprised us. We saw actually into the lava a little bit. and what we can learn about Io from this instrument. The next speaker will be Alessandro, who is the lead scientist for our infrared camera that's built in Italy. And he's going to be staying on this topic of Io when we flew by close, but we also monitor Io from a distance. And we monitor this most volcanic body in the solar system and see all of its activities. And so he's going to be talking about what we've learned from this infrared instrument about how the volcanoes on Io work, how they're similar or different from that on the Earth. And then the next speaker is Yohai, who's going to go back to Jupiter and talk about the polar cyclones. So over the top of Jupiter, both poles are what we call polar cyclones. The south has one number, and they're all kind of arranged in a geometric pattern. This is one of these polar cyclones kind of close up. It's a very beautiful hurricane-like feature. He's going to be talking about how these hurricane-like features work, what makes them stable, how they move, what we've learned about the polar atmosphere of Jupiter, and also talk about the fact that as this orbit migrates that allowed us to go and see the satellites, Jupiter's been moving around the sun, and we now are going behind Jupiter. Our original mission stayed only up front where we're solar powered. We wanted to be pointing at the sun all the time and get data or get energy. And now we're actually passing behind Jupiter, and we get to do an experiment called occultations, where you can learn about the upper atmosphere. So he's going to explain how that works and what we hope to learn and what we've already learned a little bit from this. So with that, I'll pass this on to Shannon.
All right. Thanks, Scott. So, Shannon Brown from the Jet Propulsion Laboratory. I've been involved with Juno for a little over 20 years, and probably one of the most exciting missions I've been involved with, because every time we orbit Jupiter, we learn something new, and recently learning a lot new about the moons, which I'm going to talk about here, and I'll share some exciting new results from the microwave radiometer. So this instrument, as Scott said, was designed to see uniquely down deep into the Jupiter's atmosphere, hundreds of kilometers deep. We do this using 6 different wavelengths, ranging from 1 centimeter to 50 centimeters, so very short to very long. And that longest frequency allows us to see very deep, hundreds of kilometers into the Jupiter's atmosphere. And to do this, we need very specialized instrumentation, particularly to survive in Jupiter's environment. Not only that, because we're measuring at a long wavelength, the antenna has to be huge. It actually drove the size of the spacecraft and was about as big as we could fit into the rocket. Not only that, it probably looks a little unique if you're used to thinking about like microwave systems, like say a satellite TV dish. An all-metal design, and the reason for that is we started out with a more traditional design for the antenna, but we realized that as it was going to be circling Jupiter, it was going to build up charge and start sparking, and that's certainly not something that you would want to have happen to your instrument as you're going around. So the engineers came up with this really unique design that was specially designed for the Juno mission that it's been operating very successfully in the 9 years that we've been orbiting Jupiter. So what we've been able to do, so most of our early mission observations where the orbit was much closer to the equator had focused on understanding the deep atmosphere at the equator, temperature and the composition. But as the extended mission progressed and the orbit moved closer to the poles, we've been able to really take the microwave instrument and look more closely at these very dynamic storm features that are circling the North Pole. And you'll hear a little bit more about them at the end of the briefing from Yohai. These are big circumpolar cyclones. It's very similar to hurricanes here on Earth, except they're much larger. They're about the size of Australia. And they circle the North Pole very slowly. And now we're finally able to resolve them with our microwave instrument. So before we knew about how big they were in horizontal extent, but now we can see just how big they are in vertical extent, how deep they go. And it turns out they're not only big horizontally, they're huge vertically, about 10 times the size of hurricanes that we have here on Earth. The microwave instrument, it's not shown here, but also showing us where lightning is happening around these. It's happening around the edges of the storms, similar to the way it happens on hurricanes here on Earth. And pretty much, if you were on Jupiter, you wouldn't want to be anywhere near these storms. But what the results I really want to show with you is when we took this instrument, which was designed to uniquely look deep into the atmosphere and were able to look at the moons because the extended mission flew by very close by Ganymede, Europa, and Io. We've been able to then see into these bodies, these icy or rocky bodies that we had never really been able to look into before. This is the first time we'd been able to see into the subsurface of these bodies. And the power of Juno is we have multiple wavelengths, multiple instruments that can look at these bodies. So what you're looking at here are three different wavelengths from the visible on the far left side. That's what our eyes see. So you're seeing colors, topography, very high resolution imagery. In the middle, you're seeing infrared. Now, Alessandro's going to talk more about the infrared. That's showing us where all the surface heat is distributed. And then the last image on the right, that's the microwave image. So this is the first time that we've been able to see the subsurface temperature. So not just these surface features, but into the subsurface. It's kind of interesting what this has shown us. So, if you ask really anyone on the Juno project, maybe with the exception of Scott, we didn't think that we were going to see anything all that interesting with the microwave radiometer looking at Io, because we're seeing maybe 6 to 10 meters into the subsurface. If you compare that to the entire lithosphere, the crust of Io, which is about 35 kilometers or so, it's a very small fraction that we're seeing into the subsurface. So we didn't really expect to see much of a temperature difference between the shortest wavelength, which is seen very close to the surface, and the longest wavelength, which is seen, about 10 meters down into the surface. But when we looked at the data, it really surprised us. Io surprised us. What we saw was a very significant frequency dependence in that the shortest wavelengths were seeing a cold temperature, whereas the longest wavelengths were seeing a very high temperature and much increased temperature. And the way that we can explain this is if you have subsurface or near surface heating, so like, for example, a lava flow, that long wavelength observation is going to be able to punch through a crust that often forms on lava flows and see that hot magma, where the shorter wavelengths are going to see that cold crust. And just like the infrared would only see the surface, the short wavelengths of MWR would just also see that surface. So this, for the first time, is saying that there is a significant portion of Io's surface that is potentially covered with these near surface active lava flows. And we've never been able to see that before. And it's extensive. It's everywhere we looked. It wasn't just one or two places. Everywhere we looked, we saw this increased surface heat, which could be in the form of lava flows where you develop an insulating crust, just like here on Earth. And it was about 10 to 15% of the area of Io, which is about a little over half the size of Europe. So that's a lot of extent. And then the other thing that we've been able to infer from the microwave data is the surface is very low density, very similar to like a volcanic pumice rock here on Earth that forms when magma cools and gases evaporate and expands like a sponge, and it's less dense than water. You can see an example of that floating in water. So we're not saying that it's exactly pumice, but it just appears to be a low density material like perhaps dust or a very low density rock. So this is very unique. We've never been able to see into the subsurface of any of the moons before, and this is the first time that we're looking beneath the surface of Io. So now I'm going to pass it on to Alessandro, who's going to continue the discussion of Io and tell you more about what the infrared observations are telling us.
Thank you, Shannon. Alessandro Mura from the Italian Astrophysical Institute, and now I'll talk you a little bit more about the volcanic moon of Jupiter, Io. So as Scott told you, Io is the most volcanic object in the solar system, not only for the amount of volcanic centers, but also for the energy they release. So the interior of Io, according to our observations, is completely filled by magma chambers. They are scattered all over around, more or less the same way that a sponge is filled by holes. And these magma chambers are energized because of the enormous tidal interaction with Jupiter. So being Jupiter so big and Io so close to Jupiter, basically the Jupiter deforms Io, it squeezes it. And this energy has to go somewhere, and it goes to the surface where eruptions occur. Okay, so during orbit 68 of Juno, the Gherman instrument, the infrared Gherman instrument on board Juno, had the chance to observe something really unexpected. It is the largest eruption ever recorded on Io, that probably matches the largest eruption ever recorded on the Earth. you have to remember this is infrared light. So as Shannon told you, infrared is very good because it's not visible to our eyes, but it gives you the amount of energy, the amount of heat that the body is releasing. So it's very useful for this purpose because it's able to tell you the energy budget of something. Okay. So thanks to this data, we were able to measure the energy, total energy and total power of this eruption. So the volcanic centers that we call hotspots, spots over there, and you see actually Juno measured about 200 hotspots. So they are scattered all over around. In particular, now we are going to... Okay, so thanks to this data, we were able to measure the total energy and total power of this eruption, which was huge. It was 300 terawatts. I would like to give you some context. 300 terawatts for several weeks is the same amount of energy that the total human civilization uses for 1 year. Okay. If you want to compare this energy and power with a volcano, so this matches very well, for example, with Mount Tambora eruption in 200 years ago, the age of Napoleon, basically. So what is this telling us? It's telling us that what is occurring every hundreds of years on the Earth, so it's very rare, on Io occurs very often because the previous record for an eruption was set on Io only 20 years ago. Okay, now this is the new record. What is even more surprising is that we observed that at the same time, many eruptive centers, many volcanoes, what we call patera actually, were erupting simultaneously with the central one. So actually, this region that was interested by this simultaneous eruption was very huge, the same size of France, 500,000 square kilometers. It's just like if France is filled by volcanoes and all of them are erupting all together, which is surprising because they need a system to communicate each other. So what we learned from this, we learned that the subsurface of Io, the immediate subsurface, should be filled by magma chambers, which are interconnected by magma channels or tunnels or pipes, whatever, so that they can talk each other and they share information about pressure changes immediately.
Hi everybody. Going back to Jupiter, I'm Yochai Kaspi from the Weizmann Institute of Science in Israel. I've been a member of the science team of Juno for the past 17 years, working mostly on gravity and atmospheric science. And today I'll talk to you about some very exciting atmospheric science results that we've been getting for the past months in the extended mission. And the reason that we can get this new and exciting result is the fact that Juno, for the past 18 months, has gone into this unique orbit where every time we go around the planet, we pass behind the planet from the point of view of an observer on Earth. So from an observer on Earth, if you want, Juno basically sets and rises behind the planet every time. And this orbit gives us the opportunity to do radio occultations, which is basically an experiment where we send a radio beam from the spacecraft to Earth, and as it goes as the spacecraft sets and rises behind the planet, for an instance, this radio beam goes through the atmosphere. When the radio beam goes into the more dense medium, then the radio beam gets bent. And what we do is measure this bending of the beam and interpolate that to understand the density and temperature structure of the atmosphere at every one of the points where this is happening. This experiment was actually done in the past by Voyager and Pioneer back in the 70s, but since then, for over 40 years, this was never done for Jupiter. And with Juno, we have much more orbits and opportunities to do this than before. In the 70s, we had 6 such measurements, and now with Juno, we already done 26. So we have 26 profiles, and we continue doing this every orbit, every time the spacecraft sets and rises around the planet. And what's special about this experiment is that this is an experiment that basically happens over 800 million kilometers. We're not only sending the beam from the spacecraft, but then we need to monitor it from Earth. So and then see how it changes. So we're measuring these tiny little changes in the bending, and changes in the frequency of the beam, and then we can interpolate this to get these temperature profiles of the atmosphere. This all exists high above in the stratosphere. Now, if we dive down below and we go down to the cloud layer, then we can see these circumpolar cyclones that Shannon mentioned before. And we have 8 such cyclones surrounding the polar cyclone in the north, and 5 such features in the south. And these are really unique features that we see only on Jupiter. It's the only planet in the solar system where we have these circumpolar cyclones. And what's new here is that since we've been tracking these features for almost 9 years now, since the arrival of Juno Jupiter in 2016, then we're getting more and more information about the movement of these things. We see them kind of drift around over these 9 years, and they also bounce around each other. And with tracking them over time, we've now been able to understand the physics of what's holding these cyclones together and why are they there from the first place. As mentioned before, these are just like hurricanes on Earth. These are cyclones. They rotate in a cyclonic fashion. They're fueled from below, from the heat, but different than hurricanes on Earth, which exist in low latitudes and are kind of singular features. We never see a few of them clustered together. On Jupiter, they all cluster together. Now, like hurricanes on Earth, cyclones have a tendency to drift towards the pole. In the Jupiter case, they all drift and converge towards the pole until they basically bump into one another. But then when they get too close, they feel the other cyclones and they just can't get close together. The way to think about this in a simple way is to think about this as a system of springs. So again, they have this beta drift which pulls them towards the pole, but they can't get too close because of the existence of the other cyclones, and then they kind of basically bounce together. They bounce in a sense that they have a 12-month oscillation, so they drift constantly westward and also oscillate around themselves. And what we've been able to do now is by monitoring these motions over these 72 orbits of Juno, we can really track the physics, explain how these work, and then explains not only cyclones on Jupiter, but actually cyclones on general, a phenomenon that we don't have on Earth. So on Earth, because of their isolation, it's hard to learn about interaction between hurricanes or cyclones. On Jupiter, we've been able to do this.
88.3 Southern FM. The sounds of the Bayside.
Several weeks ago, we here on the Space Show promised to keep you updated on the progress of the Swift Reboost mission.
NASA is working with an American startup to attempt something no one has ever achieved. Boost a spacecraft before it re-enters the atmosphere.
This is just a really different kind of mission. We can't wait long.
Its orbit has been lowering. If we do nothing, Swift will re-enter the atmosphere, and so there's nothing to lose.
Just a few months ago, this spacecraft was a conceptual drawing.
Catalyst's robotic spacecraft will approach the observatory, carefully capture it, and propel it to nearly its original orbit.
6 months ago, this was a PowerPoint, and it looked nothing like this. In under a year, we're going from identification of a problem, proposal, contract award, to launch.
Saving Swift isn't about just preserving one mission. It's about moving forward in a future where we can give spacecraft a second life.
At first, all seemed to go well, as NASA reported on July the 3rd.
A mission to raise the altitude of NASA's Neil Gorel Swift Observatory is underway after launching from the Marshall Islands on Friday, July 3rd, from Kwajalein Atoll in the South Pacific Ocean. Link, a robotic servicing spacecraft built by Catalyst Space, launched into orbit on a Northrop Grumman Pegasus XL rocket, which was deployed by the company's Stargazer, a modified L-1011 aircraft, an altitude of about 12.2 kilometers. Our planet's atmosphere creates drag for spacecraft in low Earth orbit, gradually reducing their altitude if they don't have propulsion systems to maintain their positions. Recent solar activity magnified this effect on Swift, and its orbit decayed faster than anticipated. Now that Link has reached orbit, the Catalyst team's first step is to acquire a signal from the spacecraft, confirming its solar panels have deployed and the power systems are working.
On July 15, things were all good.
teams continue to progress through in-orbit preparations for the robotic servicing spacecraft designed to boost the Neil Gorel Swift Observatory to a higher altitude. Catalyst Space's Link spacecraft remains healthy and is about halfway through this commissioning process. Link launched July 3rd, completed its initial post-launch sequence, and began system checkouts. After completing solar array deployment and establishing communications, Catalyst now has commissioned Link's power systems and avionics, as well as conducted propulsion system checkouts. This has involved firing the spacecraft's xenon-fueled thrusters, which will be used to travel to Swift and slowly raise its orbital altitude over the course of several months. The Catalyst team also quickly addressed early communications and attitude control issues seen during flight operations, including an issue with one of the spacecraft's 3 reaction wheels. After identifying the cause, they implemented flight, software patches, and operational updates that restored reliable communications and stable attitude control. The commissioning process will continue over the coming weeks, with flexibility built in to allow the team to pause, assess data, and adjust as needed. Link then will begin its transit phase to meet up with Swift.
Then, on July 28, came news that no one wanted.
Over the weekend, Catalyst's Link servicing spacecraft experienced issues with attitude control, causing the spacecraft to spin and resulting in sporadic communications. Preliminary investigation shows that 2 of Link's 3 reaction wheels currently are not operable, and there is some loss of functionality in its cold gas thruster system. Link's other major subsystems are functioning as expected. The spacecraft remains power positive and in communication with the Catalyst team. The team is working to stop Link's spin over the next few days, using the spacecraft's electric propulsion thrusters. After reestablishing stable attitude and further investigating spacecraft status, Catalyst plans to update Link's guidance, navigation, and control to accommodate the spacecraft's new configuration. Working closely with NASA teams, they will then evaluate revised plans to approach and capture Swift, depending on safety of the approach and Link's health.
3 days later, there was an indication that the mission might be able to be saved.
Teams at Catalyst Space are making progress slowing the spin of their Link spacecraft, which is designed to boost the orbit of the Neil Gorel Swift Observatory. A series of thruster burns this week reduced the rate of spin from approximately 9 degrees per second to less than 4 degrees per second. Catalyst is continuing with this approach to re-stabilize the spacecraft in the coming days. Teams also further evaluated Link's functionality and determined there are still potential paths forward for a boost. NASA is working closely with Catalyst to consider revised, innovative approaches. Link is now expected to approach Swift around the end of August.
And we'll keep you updated as to how that goes. They've saved missions before. Think Apollo 13, for example.
The sounds of the Bayside, 88.3 Southern FM.
Gherman Titov made his flight some years ago now, 1961. What happened was he was born in 1935, September the 11th, in the Altai Krai region of Western Siberia. And he made the Vostok 2 mission in 1961, August the 6th through to the 7th. And at the time, he was aged 25 years, and he's still the youngest astronaut, professional astronaut ever. And the flight duration was 25 hours and 18 minutes, which was a pretty amazing thing to happen at the time. And he died in 2000, September the 20th, in Moscow, aged 65. And if you think that's rather young, well, he was poisoned by carbon monoxide from his home sauna in his flat in Moscow. There is a crater on the lunar far side which is named after him. So let's go out with that music that we just heard about Titov. Well, you've been listening to The Space Show with Andrew and Richard, and we'll be back next Wednesday at 7 o'clock to bring you more news from what's happening in space.